Okay, we are in chapter 7. We are looking at connections, and I just wanted to go over this problem briefly. We talked in class a little bit about tables, like in the steel manual, that you could get section properties for different shapes. And so we have a W310 by 60 steel beam. It has a channel, a C250 by 45 channel bolted to the top flange as shown. The beam is supported at its ends, okay, and it carries a concentrated load of 100 kilonewtons in the center. So that sounds like a simply supported beam if I've ever heard one, okay, of 100 kilonewtons in the center. So I went ahead and from another table, I went ahead and pulled what the equations for a simply supported beam loaded in the center for your shear and your moment of a 6 meter span. So this entire length is 6 meters. So we're at 3 meters and 3 meters. Okay, but our entire length equals 6 meters. So that would come here. We have 6 meters. Our P is going to be 100 times 10 to the third newtons. 100 times 10 to the third newtons. Pairs of 24 millimeter diameter bolts, okay, are spaced at intervals S along the beam. So down the beam, S, 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 we're going to see these bolts. If the allowable shear stress in the bolts must be limited to 125 megapascals, determine the maximum spacing interval S for the bolts. Okay, so if we are looking at spacing and shear, then we are going to be looking for our shear flow is VQ over I. And our Q, our shear flow, is the force of our fastener divided by the spacing. And in this case, we have 2 fasteners, 2 forces of fasteners divided by spacing. So we know that the allowable shear stress in the bolts is given, as 125 times 10 to the 6th Newton per meter squared, because we're at a megapascal. And shear stress comes from V over A, okay? And this V, so when I look at that, that shear stress is going down the lengths of the beam. It is wanting to shear that bolt right there. Shear that bolt right there. And so we are going to figure out then how much force is actually allowed by this allowable stress. So our area, we have 2 bolts, pi over 4 d squared, 0.024 meters squared. And we can now come back and figure out what this value is that's going to be the allowable force of the bolt. Because they didn't give us the force of the bolt, they gave us the shear stress. So the allowable shear for 2 bolts combined is going to be 125 times 10 to the 6th Newton per meter squared times 2 pi over 4, 0.024 meters squared. And that allowable shear force that we can have is 113,097 newtons. Okay, 0.097 newtons. So this would be the total allowable with those 2 bolts. If I wanted to look at 1 bolt then, and we could then, so this is what is going to be allowed. What do we have? We have P over 2, 100 times 10 to the third newtons divided by 2. So we have 50 times 10 to the third newtons is the shear that we have actually going up and down that beam, okay? Up and down that beam. And this is going to be the force of our fastener. That's going to be the shear force that is allowed, okay? That's the shear force that's allowed based on my allowable stress. So remember that shear is going through and it's going to want to cut that bolt right in half. So when I have force of the fastener divided by spacing equals VQ over I now know that the force allowed by a fastener is 113,097 newtons. And again, we That takes into account both of my bolts. The shear force that we have is 50 times 10 to the third newtons. Our moment of inertia is given as 204,136,153 millimeters to the fourth, so we need to check that unit. And now we've got to figure out what is Q. So Q is going to go from the centroid to the centroid of the piece that we're holding. And this is what I want to show you. This is a different table, but when you're looking at a table, you are given information about the channel. You have the cross-sectional area. We have D, which is the height. We have the thickness of the flange. We have the thickness of the web. And then we have the moment of inertia about the X and Y axis. But what I need right here is this distance that goes from the outside to the centroid, this depth. Do you see that depth? That is XB. And for this section, our XB is equal to, I had it written down and now I can't find it, is equal to 16.3 millimeters. So I know when I'm looking for the Q that I have to go up this height, and that's to the top. That's 103.012 millimeters. And then the centroid of the channel is going to be about there. And this distance is 16.3 millimeters. So the distance from the overall centroid to the centroid of the channel is going to be 103. Where's to the top? 103 minus 16.3. Okay, minus 16.3. And when I'm looking at Q, then it is the area that I'm holding on, times its moment arm. So again, you can go back to, this is a different table, but I can actually get the cross-sectional area from a steel table. Okay, I can get that cross-sectional area. And I find that the area is 5,680 millimeters squared. Again, that C value coming back down was 16.3 millimeters. So as I'm trying to find Q, it's going to be the area times Y bar to the top minus C. Okay, and that's going to be my Q. So now we have everything we need to plug in to find the spacing. So the force of our fasteners, we have 2 fasteners. I doubled the area. We are allowed 113,097 newtons. That was based off the shear stress, which is force over area. We are looking for spacing. Our shear that we have is 50 times 10 to the third newtons, because part of the shear goes, part of this P goes to the right, part of it goes to the left. When I'm looking at Q, it is the area of the channel. That's what I'm holding on to. That's in millimeters squared. So I'm going to have to divide by 1,000 times 1,000 to get this to meters squared. And then times, okay, times to the top is 103.012 millimeters minus 16.3 millimeters. Okay, that gives my moment arm, but we've got to divide that by 1,000 to get it into meters as well. Divided by moment of inertia, and it gave us the moment of inertia of that whole system. 136,153 millimeters to the fourth, so we need to divide by 1,000 to the fourth, okay? And then we can go back and calculate this spacing, okay? We can go back and calculate this spacing. And so when I do that, I get a spacing of 0.9375. And let's think about our units. We are in newtons. We have converted millimeters to meters, millimeters to meters, millimeters to meters, meters. So if we wanted to look at millimeters, 937.5 millimeters. And again, this is the max that it can be, maximum. So we might round down to, 900 millimeters on center, because we want to round down. But that's how you can use a steel table if you're given these sections, is you can get their areas, you can get their dimensions, you can get to the centroid, their moment of inertia. So somebody, you guys aren't doing this, but you could, would have to find, if this is a built up section, well, where is the centroid? Well, I'm going to have, I have to find the centroid from the bottom. So I'm going to have the area, which I can get off of here, times the distance, which I can get that centroid distance, plus the area, again off of a chart, times its distance from the bottom, divided by all of the areas to get y bar. And then remember, we would have Ix plus AD squared. So I can get my moment of inertia about itself, plus area. Again, here's my area. And then the distance from the centroid of the hole to the centroid of the piece. And all of that can come from steel tables.